Good afternoon. In this video, I'll be discussing the CSSA 2010 extension question 7b. In this question, we have a circle geometry question involving two circles. And the first thing that you need to do whenever you have these questions is to read the wording of the question and spot anything that is not actually drawn in the diagram provided to you. This is why I've copied the diagram onto my booklet so I can do whatever I want with it. Let's start off by reading the question. Two circles intersect at P and Q as shown. The center of the smaller circle is H and the center of the larger circle is O. H, O. The smaller circle passes through this center of the larger circle, which it does. The tangent to the smaller circle at P, this line, RPT, cuts the larger circle at T. The chord in the smaller circle, this chord PQ. Now this PQ is not necessarily a diameter, it's just that the way I've copied the diagram with my compass has caused it to look like a diameter. Now if this causes any issues later in the question, you're going to have to redraw the diagram. But for now, this chord bisects the angle PQ bisects angle RQO. Now this is not something that is seen in the diagram. In fact, you see no evidence of it in the diagram, but it is given to you in the question. So what you must do is add it to the question, add it to the diagram. So what we have here, we have RQO is bisected by the chord PQ. Now the best way to actually demonstrate that is probably by labeling it with a dot, like so. Okay, just so we can all see that these two angles are equal. Now, of course, on a better diagram, OQ and TQ would look a bit further apart, but here, because I'm using a different color, it makes it more obvious that this angle here is OPQ, not TQP. Sorry, OQP. Now, the first part of the question asks you to prove that triangle PQT is isosceles. Now, there are several ways to prove something's isosceles. You can either try to look at this triangle and go, can we prove that TP is the same as QP in terms of length? There's not a lot of length going on here. Another thing, since they labeled alpha for you already, then our goal would be to try to prove this is alpha. So your goal really here, you can write goal. Another way you can write this is required to prove that angle PQT is alpha. Now, how do we get this to be alpha? We can't write alpha here because we don't know what it is. And if we ever labeled it as alpha before we got to prove anything, we might end up using things we're trying to prove, which is called a circular argument. You don't want that. So we must start here. We must somehow travel from here and make a journey around this diagram so that this...
sorry for this interruption, teachers and students. Just letting teachers know that at 3 o'clock, Brother Patrick would like to see the whole school in the Morley Plaza. So at 3 o'clock sharp, so all boys will be sitting down in the Morley Plaza at 3 o'clock. A bell will ring at about 6 minutes to 3 so we can be there at 3 o'clock. So please be prompt. Thank you.
Thank you very much, Mr. Stevens. Now, let's start off from alpha over here. This alpha is not part of the small circle, nor is it really anything to do with this tangent because it's not part of the small circle. So we must first look at this alpha in respect to the big circle. Fortunately, this alpha is subtended by PQ, which also subtends this angle at the middle of the circle. It subtends POQ at the middle. So what will actually happen is that you're going from angle PTQ towards angle POQ, and the relationship between those two is that this is 2 alpha. Angle at the center is twice the angle at the circumference. Now, having done 2 alpha, now we can look at this angle 2 alpha and go, well, now that is part of the smaller circle. In fact, not only is it part of the small circle, it's subtended by PQ, which also makes an angle okay, it makes an angle of QPR with the tangent of the small circle, and by alternate segments, that is also 2 alpha. Now we can now say that that is the exterior angle of those two, and therefore we can now say that angle TQP is what we want. I'll leave it up to you to write the proper proof of this on paper. Okay, now part 2 of the question, they are asking you to prove that P is the midpoint, so P bisects the interval R and T. Now, R is really sort of a pretty arbitrary point. If you ever thought about the fact that P could bisect sort of RT, then earlier on, didn't we just say that this line is a tangent? So R could be anywhere, right? R could be closer to P, further than P. What's to make R at a point that P can bisect TR? What is something in this question that is provided to us, some information that we have not used? This is a question that you must always ask yourself when you're doing the harder circle geometry questions. What is something that you haven't used? This. It's also this very same thing that was sneakily left out of the diagram, either because they didn't think it will make the diagram look nice, or because they just hid it in the paragraph and hoped you wouldn't see it. So PQ bisects RQO. Now, what does it mean in this case? You see, when you want to prove that this point P is the midpoint of these two, you ultimately want to prove that these two lines are equal. Now, what we already know is that from part 1, these two lines are equal, right? We already know that TP equals to PQ. So if we can prove that PQ is also equals to QR, then we're on the right track. But if you want to prove that, that's the equivalent to proving that triangle PQR is also isosceles. And the way that it's isosceles is that somehow this angle that I'm labeling in green should be equals to that angle that I'm labeling. How are those two angles equal? Now, if I gave you a sort of a triangle and you were focusing on this particular triangle and one of the angles is 2 alpha and you want these two angles to be equal, well, these two angles have to be a certain value. In fact, 180 minus 2 alpha divided by 2, 90 minus alpha. So your aim here is to prove that that is 90 minus alpha, because once you can prove that PQR is 90 minus alpha, then the rest falls through, because if that's 90 minus alpha, you can conclude that that is also 90 minus alpha just using the angle sum of a triangle, because we got 2 alpha here labeled as we progressed through question part 1. How do we prove that that's 90 minus alpha? Very easily, because what actually happens now is that you start from part of the working out from part 1. You start from the fact that angle POQ is 2 alpha. So one of the base angles, angle OQP, is half of 180 minus 2 alpha. And then you realize that according to the information given to you in the pink, that will give you angle PQR on a plate, pretty much. These two pink dots. And that pretty much equals to 90 minus alpha. And then after that, all you have to do is just a bit of conclusions. And the conclusion is that because that's 90 minus alpha, that's 90 minus alpha, that is 90 minus alpha angle sum of a triangle, that is an isosceles triangle, those two are equal, those two are equal from before, those two are equal. I'll leave it up to you to write the proof out. Enjoy.